Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to cover this idea of electromagnetic radiation by taking a step back from specific wavelengths to talking about this idea that you can have many, in fact, a continuum of wavelengths that are going to be measured or defined by their wavelength. Okay? So to pick up where we left off last time, right, we had laid out this idea of electromagnetic radiation as being this wave moving in a particular direction at the speed of light, and that we could characterize this wave with wavelength being the distance from one peak to the next, or frequency, which was the number of peaks that passed by a given point in a given period of time. And we had ended the last video with these three equations that showed that wavelength and frequency were both related to the speed at which the wave was moving, but they were actually inverse of each other, meaning that if you increased one, you decreased the other. And I started the video by saying that wavelength, right, this idea of lambda, which looks like an H, right, is fundamental to remote sensing. Now I want to talk about why it's fundamental, and why this measurement from one peak to the next is so important. Let's give ourselves a little bit of room here. And I want to talk about this idea of the electromagnetic spectrum. Electromagnetic spectrum. Right. And so as the name implies, right, we're dealing with electromagnetic radiation, right, and the concept of a spectrum, meaning that we don't just have one static wavelength and frequency, right? As we set those equations up, right, we left them as variables for a reason, right? We knew that the speed of light was constant, but the other two pieces, right, wavelength and frequency, could fluctuate. And when we fluctuate wavelength, right, we create a continuous spectrum of possible wavelengths. So what we're talking about here is this idea that we can measure or know something about this spectrum of different wavelengths of electromagnetic radiation. Okay. The key thing here to think about when we think about the sun or the human body or anything else that has a temperature greater than absolute zero, right, is that they don't emit just one wavelength, right? They emit a spectrum. And so what we've done as scientists is we've taken this spectrum of wavelengths and we've broken it up into several key regions. Okay, so what I want to do quickly is just go through some of the key regions and then talk about the ones that are most important for remote sensing. Right, so wavelength is increasing in this direction. Right, so this is increasing wavelength. Right, so if we start out over here, right, at low, very short wavelengths, right, we have gamma rays. Right, so if you're familiar with the popular Marvel universe, right, gamma rays are the things that give the Hulk his power, right? Hulk smash, that comes from the idea that he was bombarded with gamma rays, which are really just extremely short wavelength electromagnetic radiation. Right? Moving to longer wavelengths, right, we get to the region called X-rays, which probably seem familiar to you because X-rays are used in X-ray machines. Right? So when you go to the doctor and they use an X-ray machine to get a view of what's happening underneath your skin, what they're actually doing is they're bombarding you with X-rays and then figuring out, and we'll talk about this in the next video, the mechanisms here, they're actually measuring the amount of the X-rays that bounce off your bones because X-rays go through the skin to figure out what your bones look like underneath your skin. Right? And so as we move up again getting longer wavelengths, right? The distance between those peaks is increasing. We get to something called ultraviolet. Right, so ultraviolet, if you are thinking in terms of the next region that we'll talk about, right? Ultraviolet is the stuff that's just shorter in wavelength than blue. A lot of flowers do a lot of really interesting things with ultraviolet. Right? A lot of insects, especially a lot of bees in particular, can actually see ultraviolet, and it helps them identify different parts of a flower. Right? There's a strong evolutionary interaction between insects and flowers wrapped up around this idea of ultraviolet electromagnetic radiation. Okay? So I'm going to put a red line here. Okay. Probably should have put a blue line, but that's okay. That's a joke you'll get in a second. Right? On the other side of ultraviolet, right, we have what's called the visible spectrum. Right? And it's called visible because, as the name suggests, right, the visible spectrum is the light that we can see, right? So visible, right, this is what humans are evolved to see, right? So if you think about a rainbow, right, Roy G. Biv, red, green, blue, indigo, violet, right, all those colors, those all actually fall in the wavelength region of the visible spectrum, okay? Beyond that, we have what's called infrared. And I'm going to put another line here, which will be clear in just a second. Beyond infrared, right, we have microwaves. So whenever you use a microwave to cook popcorn, melt butter, right, do whatever it is you're trying to do, maybe you're making ramen, right, microwaves, what happens there, right, is that the machine is engineered to produce microwaves. Those microwaves then interact with the molecules in the food to make them heat up, which again is something that we'll talk about next video in terms of the mechanisms there. And then finally, right, we have two more regions that I want to talk about. If we give ourselves a little bit more room here, right, after microwaves, we have radio waves. Right, radio waves are if you think about when you're driving in your car, right, and your car has a little antenna on it that's picking up the radio, right? Radio waves are actually not the radio waves, the radio, right, the tower that is sending the signal, that signal is being transmitted on electromagnetic radiation that is specifically at the wavelength region of radios. Okay, so I broke these up with red lines here because this region right here, visible and infrared, this is the primary remote sensing region. Right, this area here is the area where most of the things that we're going to be talking about, most of the wavelengths that we're trying to sense with the remote sensing are going to be coming from. So what I want to do is I want to actually break this out. And in particular, break down a couple of key areas in this remote sensing region that we're going to need to be concerned with. Because in this module and the next module, right? When we talk about this idea of bands, which we're going to get to in the next video and we're going to be focusing on a lot in the next module, when we say something like, oh, band 2 is blue, right? We need to know what that means. And so what I want to do is I want to lay the groundwork for that now. So what we're talking about for the remote sensing region is basically the region from about 400 nanometers to about 3,000 nanometers. Right. And so what I want to do is I want to break this up into a few key regions that are sort of, you can think of them almost as buzzwords. Right? So when you see somebody say one of these buzzwords, you'll immediately be able to convert it into the necessary wavelength region. Right? So if we start at 400 nanometers, so approximately 400, and I'm putting approximately here because depending on who you talk to, right, the numbers may vary slightly differently, and maybe somebody will call it something and it's kind of on the edge, right? But from approximately 400 nanometers to approximately 500 nanometers. Right? If the wavelengths are in this wavelength region, right, we typically call this blue. Right? And so again, right, we're talking about a spectrum here. So over here would be blue. Over here you might start seeing something more of like a purple, right? But generally speaking, if it's in this range, we call it blue, right? So from approximately 500 to approximately 600, right? If it's in that region, right, we call that, let's make it actually legible here, right? We call this region, generally speaking, green, right? And again, right, the closer we get to here, right, this area here in the high 500s, right, we might start to think of that more as yellow, right? So we have greens and yellows in here. Then we have from approximately 600 to approximately 700. Right, in this region, we have our reds. Right, and again, lower region you might think of as being more orange. Because again, this is a spectrum, but broadly speaking, right, reds, greens, and blues. The next one I'm not going to use a color for because there really isn't a color equivalency. But this very narrow region from about 700 to about 900. Oh, actually, probably even shorter than that, honestly. From about 700 to about 800. Right, this region here, this is what's called red edge. And the reason it's called red edge is because it borders the red, but it also borders the next big piece we're going to talk about, which is near infrared, right? So in this little 100 nanometer-ish region here, right, again, because this is a spectrum, right, I'm breaking it up into pieces, but it is a spectrum, right? You have influence of both the red, whatever is impacting the red, as well as whatever is impacting the near infrared. Right? So then what we have is from approximately 800-ish to approximately 1100, right? This region here, this is your near infrared, near infrared, or NIR. Right? And then finally, the last piece here, from approximately 1100 to approximately 3000 nanometers. Right? I'm gonna do this in a different color. I'm probably gonna regret this. Right? But this region here, right? This is your short wave infrared, or you'll often see it abbreviated as short wave infrared, or SWIR, SWIR. Okay? So, taking a step back, what we've done here is we've looked at this idea of electromagnetic radiation having that specified wavelength, but remembering the fact that it's not just one specific single wavelength, rather, right, anything with a temperature above absolute zero is going to be emitting a spectrum of these things. And what we've done is we've, as scientists, broken that down into ranges, right, what are called regions. And with remote sensing in particular, we're worried about this idea of 400 to about 3000, right? Most of the wavelengths that we're going to be concerned with fall into this region. And so as remote sensing scientists, right, we further subdivided it to the blues, the greens, the reds, the red edge, which is the region between red and near infrared, and shortwave infrared. Most of the time, when you're dealing with remote sensing data, it's going to be referring to one of these regions here. So knowing these numbers, right, committing these numbers to memory, is going to be very important in being able to go back and forth between the different types of remote sensing data and what they mean. Okay? So as always, if you have any questions, please reach out. Thank you.